Alright, this is our circular motion review. We have a few different topics in here: circular motion, torque, and harmonic motion is going to be thrown in here as well as universal gravitation. So we have a few different topics that are all related. They all have to do something with circular motion. Uniform circular motion means we're moving at a uniform speed at a constant radius. We're accelerating even though we're moving at a uniform speed because the direction is changing. We have a change in direction. And if you remember from a couple reviews ago, anytime we have a change in direction, we have an acceleration. We call the acceleration, it has a special name, it's called the centripetal acceleration. Centripetal means center seeking. And that's a good way for you to remember that when something is moving in a circle, the acceleration is pointed towards the center. The equation is v squared over r. Now the force in circular motion is referred to as the centripetal force. Now this can be due to just one force. Say I'm swinging something on a string. The centripetal force would just be the tension. Or it could be due to multiple forces. If you have multiple forces, what you want to do is take the in forces and subtract the out forces. Now the centripetal force isn't a type of force. It's not a type of force. So you would never draw it on your free body diagram. It's not a type of force. It's just what we call the net force when something is going in a circle. We use the equation mv squared over r for centripetal force. Here's an important point. Since a centripetal force always acts perpendicular to the velocity, the centripetal force does zero work. So if something's moving around in a circle, say I have some mass moving around in some circle, the force is always directed towards the center, and the velocity is always directed tangent to the circle. And since these are at a 90-degree angle, the work is always zero from the centripetal force. Give this problem a try. Pause your video. When you're done, go ahead and play the video. Go ahead and pause now. Okay, you should have attempted this problem. We have a coin that's on a turntable. The table is spinning. We know how far the coin is from the center. First, what we want to sketch on this diagram is the instantaneous acceleration and the linear velocity vectors. So if you remember from earlier, acceleration is centripetal. So acceleration always points towards the center. And velocity is always pointed tangent to the circle. This is the velocity. Okay. This is not a free body diagram. Don't confuse this with a free body diagram. I'm just showing you the acceleration and the velocity directions. Now we want to determine the linear speed. We can find the speed from distance over time since it's moving at a constant speed. The distance for one rotation is the circumference, 2 pi r, over the time for one rotation. We know the radius, 2 pi times 0.14 meters, divided by the time it takes for one revolution. That's 1.5 seconds. And when I do that, I get a speed of approximately 0.59 meter per second. Now the disk starts spinning faster and faster and faster, and the only thing that's keeping it from slipping is the friction. But we want to know, what is the fastest speed that the disk can turn until it just begins to slip? So let me draw a quick, this is a side view, drawing a free body diagram for this little coin. So we have a weight force, mg, we have a normal force, n, and we also have a friction force pointed towards the center, F of F. So I'm going to set up, this is how I always start a circular motion problem. I write centripetal force equals the mass times the centripetal acceleration. Okay. Next, I can write the centripetal force as my in force, which is the force of friction, F of F, equals the mass times v squared over r. The equation for friction is mu times the normal equals mv squared over r. And here, so this is my left and right equation. My up and down equation just says that my up equals my down, the normal equals the weight. So for the normal, I can replace that with mg, and I'm solving for the velocity. I want to know how fast can we go. So I'm going to cancel out the mass from each side. Solving for the velocity, I get the square root of mu g r, or the square root of 0.5 times 10 times 0.14. Plug that into the calculator. And I get a speed of 0.84 meter per second. Okay. Universal law of gravity is the force between any two masses. Remember, any two masses, it doesn't matter what they are. It could be two planets, M1 and M2, separated by some distance d. Or it could be, one of the masses could be a car, one of them could be the Earth. Whatever two masses we're using, two masses always feel a force of gravity pulling them towards each other. Here's the equation you should know. You need to know the gravitational constant, that's big G. Keep in mind Newton's third law. Even if we're talking about the force of gravity between the moon and the Earth is much larger than the moon, they both feel an equal and opposite pull. Also, when you solve problems, sometimes the problem may refer to the weight, but just remember that weight is just another term for the force due to gravity. Okay. So give the next 1, 2, 3 problems a try. Go ahead and pause your video and play it after you've attempted the next 3 problems. Okay, you should have attempted these problems. Number 40 says, what is the kinetic energy of a satellite orbiting the Earth? So here's the Earth, mass big M. Here's this little satellite, mass little m, and they're separated by a distance r. And it wants to know the kinetic energy of the satellite. What I'm going to do first is, I know that the satellite is moving in a circle around the Earth. So I'm going to write an equation for circular motion. centripetal force equals mv squared over r. Since I know this satellite is moving in a circle. Next, the centripetal force here is the gravity. So I can put in the equation for gravity. G, mass of the Earth, mass of the satellite, over the distance squared, equals mv squared over r. Now it's asking us for the kinetic energy, so we're actually going to be a little bit sneaky here. I see already mv squared. Well, kinetic energy is 1/2 mv squared, so I'm going to multiply by 1/2, both sides, and I'm going to multiply by r, both sides. Cancels the r's, and on this side, look what we have, 1/2 mv squared. So there's the kinetic energy. So I just got the kinetic energy over here, and we just look at what it's equal to. An r cancels an r, and we have G, big M, little m, over 2r. G, big M, little m, over 2r. Here an object has a weight big W when it's on a planet with a radius r. What would be the gravitational force if the object had been moved a distance 4r from the center of the planet? So here's the planet initially. We're at distance r, and then we move it so that we move it 3r from the surface so that we're at distance 4r. Force of gravity equals G mm over the distance squared. We are quadrupling the distance, so G mm over 4r squared. And let's solve a little bit more. G mm over 16 r squared. Whatever I do to the right, I have to do to the left. So the weight or the force decreases by a factor of 16. Okay. So here they give us the mass of Mars, and they give us the radius of Mars, and we want to know what is the acceleration of gravity on the surface of Mars. So I know how to find the force of gravity. It's big G times the mass of Mars times the mass of whatever object I'm talking about over the distance squared. But we want to know the acceleration. Well, the acceleration is just force over mass. So if I divide out this mass, I cancel that out to get the acceleration. So the acceleration is 6.67 times 10 to the negative 11 times the mass of Mars, which is 6.4 times 10 to the 23rd, divided by the radius of Mars, 3.4 times 10 to the 6th squared. Let's plug this in. Let's see what we get. And when I do that, I get an acceleration of 3.69 meter per second squared, or 3.7. Okay, next topic, periodic motion. This is motion that repeats itself. So think about a pendulum swinging back and forth, or an object hanging on a spring that oscillates up and down. Any motion that repeats itself over and over and over. So the two big examples are springs and pendulums. Equilibrium is the midpoint. Okay, so for a pendulum, equilibrium is that bottom point right here. This is equilibrium. At equilibrium, we have our minimum potential energy and our maximum kinetic energy. So we're moving the fastest, and we have no more stored energy. The amplitude is where we have maximum displacement. So this would be equilibrium in the middle, and both of these would be the amplitude. At the amplitude, we have minimum kinetic energy. That's because it has to turn around, so the velocity is 0. And we have the maximum potential energy. The period is the time it takes for one full cycle. So if it's a pendulum, it's the time it takes to swing over and back. And the frequency is the cycles per second. Or you just take the inverse of the period. Let's give the next 3 problems a try, all relating to simple harmonic motion. Go ahead and pause your video, try the next 3 problems. Okay, you should have attempted these problems. The first one says a particle oscillates in simple harmonic motion. Here's a graph of the displacement. At what time t does the particle have a maximum positive acceleration? So positive means up. And remember, acceleration is the force over the mass. And since this is it's a particle that's in simple harmonic motion, I'm going to assume that I can use the spring force equation, F equals kx. Okay. Now, to get the biggest acceleration possible, I need the biggest force possible. The mass is constant. To get the biggest force possible, I need the biggest displacement possible. Okay. The biggest displacement happens here and here. But since it wants a positive acceleration, if you think about this equation right here, Newton's second law, F net equals ma, the force and the acceleration are always pointing in the same direction. So where will the spring pull the object up, accelerate it up? Well, it's at 1 second. Springs always try and restore themselves. So when you pull them down, they accelerate up. When you pull them up, they accelerate down. Okay, here's our equations. Period of a mass on a spring. So a mass hanging on a spring. And period of a pendulum. Length L, spring constant K. The length of a simple pendulum with a period on Earth of 1 second is most nearly what? So I'm going to use my pendulum equation, T equals 2 pi square root of L over G. Remember, pendulum periods only depend on the length and the acceleration of gravity. They do not depend on the mass. Forget about the mass. So we're solving for the length. So I'm going to square everything here. T squared equals 4 pi squared L over G. I'm solving for the length. the length equals period squared times g over 4 pi squared. It tells me that the period on Earth is 1 second, so the length is 1 squared. Acceleration of gravity on Earth is 10 over 4 pi squared. I'll plug that into my calculator and see what I get. 10 divided by 4 pi squared. I get a length of 0.25 meters. So that's how long a pendulum would be on Earth for the period to be 1 second. So for it to swing back and forth, and that takes 1 second. The mass of the pendulum does not affect the period at all. I could hang a bus on here, or I could hang a marble. As long as the length is 0.25 meters, it'll take a second. Okay, an object swings on the end of a cord, making a pendulum. So we've got our pendulum, and another object oscillates onto a spring. So here's a mass on a spring. Also, they both have period t. If the masses of both are doubled, what are the new values for the periods? So please remember, for the period of a pendulum, 2 pi L over g, do you see any mass in that equation? The mass does not affect the period of a pendulum. So the pendulum would be unchanged. It would have the same period. So it looks like it has to be choice B. But just to confirm, the period of a mass on a spring is 2 pi square root of m over k. We're doubling the mass. If we do that, we have to also multiply the left side by the square root of 2. So as you see, square root of 2 for the mass and no change for the pendulum. Okay, last topic is torque. Torque is a twisting. It's opening a door, pushing something on a hinge. The equation that we use for torque is force times distance from the fulcrum or from the axis, that's your R, and then if there's an angle involved, you need to multiply by the sine of theta. The units you're going to get here are Newton meters. Newton meters. This is not a joule. Don't switch this to joules. Okay, I know you remember from energy that newtons times meters is joules, but not here. And normally we'll call a clockwise torque positive and a counterclockwise torque negative. Okay, go ahead and try this problem. Pause the video, replay when you're finished. Okay, you should have attempted this video, this torque problem. We're pushing on the end of, it looks like a door or something with a length L, and we're pushing on it at an angle. Okay. The torque that we get from this problem here is the force F times the distance L from the axis times the sine of theta, since we have an angle involved. That's the torque we get here. The problem is asking if the force were now applied perpendicular, so I don't need the sine theta anymore because it's perpendicular, what would the distance be to get the same torque? So the same force at some distance, I don't know what it is, but it's the same torque. Well, if it's the same torque, I can set them equal to each other. FD equals FL sine theta. Cancel out your F's, and the distance is equal to L sine theta. Okay, now sometimes you have multiple torques. You can have, you know, as many torques as 3 or 4 or 5 in a problem. And if something is not moving, we know that it's in rotational equilibrium. And so the clockwise torques are equal to the counterclockwise torques. So here's two problems in rotational equilibrium. Give these a try, pause the video, try the problems. Okay, you should have tried both of these rotational equilibrium problems. First one here, this is more of a guess and check type of problem. The answer is D, okay, position D. And what I'm going to do is just prove it to you. So this is a 70 centimeter stick. So each one of these are 0.1 meters. So this distance here is 0.3 meters. And this distance here is 0.4 meters. And so the clockwise torques have to be equal to the counterclockwise torques. Torque is equal to force times distance, has to be equal to this force times distance. The clockwise force is this 8 kilogram mass pulling clockwise. So that's going to be 8 times 10 times that distance, 0.3. And the counterclockwise torques are the 6 kilogram mass pulling this whole thing counterclockwise. So 6 times 10 to get the weight times 0.4. And if you multiply these, you will see that we get on both sides of the equation, we get 24 Newton meters. Okay. So it has to be hung at point D for the torques to be balanced. Okay, now we have this man who's walking out onto a plank. And at first glance, when you look at this problem, you may think, well, there's only one torque. It's just the torque of the man. But one thing I want you to always remember when you get a torque problem is that an object can get a torque from its center of mass. Okay, so I'm going to draw this picture a little bit bigger. Here's the plank. Here's the edge. Okay, the edge is 2 meters. There's 2 meters of plank hanging over the edge, and the total length of the plank is 5 meters from end to end. 5 meters. So that means that this right here is 3 meters, and there's some man walking out on the plank. We want to know how far from the edge can he walk. Let's call that X. Okay, the man is 50 kilograms. The plank itself is 100 kilograms. The plank's center of mass is, since it says it's a uniform plank, has to be right in the middle. So the plank's center of mass is right here, 2.5 on either side. So that makes it 0.5 meters, half a meter from the edge. So if you haven't figured it out already, this is the axis, the fulcrum. Okay, that's where the board's going to rotate if it does. So set your torque clockwise equal to your torque counterclockwise. The clockwise torque, that would be the person's torque. So that's 50 times 10 to get the weight of the person, times, we're calling it X, the distance from the fulcrum. The counterclockwise torque is the center of mass, so the person's going clockwise, the center of mass is pulling counterclockwise. The board is 100 kilograms times 10 to get the weight, times the distance, 0.5 from the fulcrum. Okay, simplify 500x equals 500, so x equals 1 meter. The person can walk 1 meter before the plank tips over.